Dear students, welcome to all of you. Today we are here to discuss atmosphere composition and stratification. First, the introduction. The atmosphere is a thick gaseous envelope which surrounds the earth from all sides and is held to the earth's surface by gravitational force. The atmosphere extends outward several thousand kilometers to a zone characterized more by magnetic fields and ionized particles than by the familiar air near the surface. Pure air is colorless, odorless, tasteless, and cannot be felt except when in motion. The air is mobile, compressible, and expansible. The air transmits compression waves and experiences tides. Transparent to many forms of radiation, it can absorb others. The atmosphere is a significant component of the biosphere as the life on the Earth's surface is because of this atmosphere. Otherwise, the Earth would have been barren like the Moon. Besides providing all necessary gases for the sustenance of all life forms in the biosphere, it also acts as a great canopy to protect the Earth's surface from the full range of solar effects and prevents excessive loss of heat. Now, the composition of atmosphere. The atmosphere is broadly divisible into two vertical regions on the basis of chemical composition. These are homosphere and heterosphere. The homosphere represents the lower portion of the atmosphere and extends up to the height of 80 to 100 kilometers from sea level. The main constituent gases are oxygen and nitrogen. Other gases are argon, carbon dioxide, neon, helium, krypton, xenon, hydrogen, etc. This zone is called homosphere because of the homogeneity of the proportion of various gases. In other words, the proportion of different gases are uniform at different levels in this zone. The heterosphere starts from the upper portion of the homosphere and extends to a height of 60,000 kilometers. Different layers of this layer vary in their chemical and physical properties. There are four distinct layers of gases in heterosphere. These are: number one, molecular nitrogen layer, which extends to a height of 200 kilometers. Number two, atomic oxygen layer, which extends from 200 kilometers to 1100 kilometers. Number third, helium layer, which extends up to a height of 3500 kilometers. And number fourth, atomic hydrogen layer, the topmost layer of the atmosphere and extends up to outermost limit of the atmosphere. The narrow transitional zone separating the two zones, that is homosphere and heterosphere, is known as homopause. Of the two atmospheric regions, homosphere is more important because living beings live in it. It contains three major groups of components. These are constant gases, variable gases, and aerosols. The constant gases are always found in the same proportions, but the variable gases are present in different quantities at different places and times. First, the constant gases. The constant gases present in the atmosphere are nitrogen, oxygen, and argon. They make up 99.96% of the air. Nitrogen alone constitutes 4/5, that is 78.08% of the air. Nitrogen is removed from the atmosphere and deposited at the Earth's surface mainly by specialized nitrogen-fixing bacteria and by way of lightning through precipitation. The elemental form of nitrogen is converted to ammonium, an ionic form of nitrogen available to higher plants by a process of nitrogen fixation. Nitrogen does not combine readily with other elements, but it is a constituent of many organic compounds. Nitrogen dilutes oxygen and thus regulate combustion and oxidation. Oxygen, although constituting only 21% of total volume of atmosphere, is the most important gas. All living organisms use oxygen. Oxygen combines chemically with many other elements and is necessary for combustion and animal metabolism. Its availability in a free state is due to continuous replenishment by photosynthesis in plants. Besides, oxygen can combine with other elements to form important compounds such as oxides. Argon is by far the least important of the three constant gases in terms of both volume and its contribution to environmental processes, constituting only 0.94% of the air. It enters the atmosphere as a result of the radioactive breakdown of potassium within surface rocks. Now the variable gases. The atmospheric gases that are present in varying amounts include carbon dioxide, water vapor, and ozone. The other gases found in almost negligible quantities in the atmosphere are hydrogen, helium, neon, krypton, xenon, methane, sulfur dioxide, iodine, oxides of nitrogen, ammonia, and carbon monoxide. Although they collectively constitute only a tiny proportion, that is 0.04% of the air, but some of them are very important and essential for human well-being. Carbon dioxide, which on an average comprises 0.03% of the air, is one of the most significant constituent of the atmosphere in terms of its climatic influence. It is very vital for two functions. The first is in the process of photosynthesis, and the second is to absorb some of the energy transferred to the atmosphere from the Earth's surface. The other absorbers are water vapor and ozone, but they are poor absorbers, and it is primarily carbon dioxide that keeps the atmosphere at temperatures that are conducive for life. Thus, carbon dioxide acts as one of the greenhouse gases that absorb heat energy. It also helps in dissolving limestone, thereby plays a role in shaping limestone landscapes. The most widely distributed variable gas of the atmosphere is water vapor, constituting between 0.0 and 4% of the total volume in cold, dry, and humid tropical climates respectively. 90% of the moisture content in the atmosphere exists within 6 kilometers of the surface of the Earth. The other variable gas found in the lower atmosphere is ozone, which is actually a type of oxygen molecule consisting of 3 instead of 2 atoms. It is produced by the recombination of oxygen under the influence of ultraviolet radiation at high altitudes to form 3-atom molecules, that is O3. The ozone is also formed by lightning discharges and by the action of sunlight on mixtures of hydrocarbons and oxides of nitrogen near the surface. It forms less than 0.00005% by volume of the atmosphere and is unevenly distributed. The great concentrations of ozone are found between 20 kilometers and 25 kilometers altitude. It is formed at higher altitudes and transported downwards. The ozone in the ozone layer filters out sunlight wavelengths from about 200 nanometer ultraviolet rays to 350 nanometer, with peak absorption at about 250 nanometers. The small unabsorbed part that remains after passage through ozone causes sunburns in humans and direct DNA damage in living tissues in both plants and animals. Now the aerosols. Aerosol is a collective term for the solids and liquid particles suspended in the air. The particles include sea dust, rock dust, few organic matters, and the products of combustion. Aerosols are particularly in higher concentration in cities and industrial areas. Aerosols, however, play an important role in initiating the formation of fog and clouds. Now we will discuss the structure of the atmosphere. Atmospheric stratification describes the structure of the atmosphere, dividing it into distinct layers, each with specific characteristics such as temperature or composition. The atmosphere has a mass of about 5 into 10 raised to power 18 kg, 3/4 of which is within about 11 kilometers of the surface. The atmosphere becomes thinner and thinner with increasing altitude, with no definite boundary between the atmosphere and outer space. An altitude of 120 km is where atmospheric effects become noticeable during atmospheric re-entry of spacecraft. The Cameron line at 100 km is often regarded as the boundary between atmosphere and outer space. The Earth's atmosphere can be divided into several layers. The different layers of the atmosphere are defined on the basis of their characteristics. Temperature is one important property that varies in the atmosphere with height. Based on temperature changes, the atmosphere can be broken into 4 major layers and another 3 small intermediate layers that serve as transition regions from one layer to the next. There is the troposphere and tropopause, the stratosphere and stratopause, and mesosphere and mesopause, and the thermosphere. First, the troposphere. It is the bottom layer of the atmosphere, subjected to differential heating, temperature inversions and convection currents, and which extends from the surface of the Earth up to a height of 8 to 10 kilometers at polar latitudes, 10 to 12 kilometers at moderate latitudes, and 18 to 20 kilometers at the equator. It contains 75% mass of the atmosphere. A very important feature of this layer is that temperature decreases with height. The rate of decrease of temperature with altitude is called lapse rate. Average lapse rate in troposphere is minus 6.5 degree centigrade per kilometer. Troposphere is the most important zone of atmosphere for the organisms. Many important climatic events such as cloud formation, lightning, thundering, etc. take place in this layer of atmosphere. Upper region of the troposphere has a narrow boundary called the tropopause, where temperature does not change with altitude. Tropopause is just like a lid over the troposphere where temperature stops decreasing with height. The word troposphere literally means zone or region of mixing, where the word tropopause means where the mixing stops. Next, the stratosphere. The layer just above the troposphere is called stratosphere, but there is contrasting opinion about the height and thickness of this layer. The average height over the middle latitudes of stratosphere is 25 to 30 kilometers, while it is estimated to be 80 kilometers by others. On an average, the upper limit of the stratosphere is taken to be 50 kilometers from the Earth's surface. Ozonosphere, a very important layer, is found within this stratosphere. Ozone present in the ozonosphere prevents the harmful ultraviolet rays from reaching the Earth, thereby protecting the life. Thus, ozonosphere acts as a protective umbrella. In stratosphere, temperature increases with height, just opposite to that in troposphere. The temperature of stratosphere increases up to 90 degrees centigrade, and such an increase in temperature is due to ozone formation under the influence of ultraviolet component of sunlight. This temperature increase with height prevents the vertical winds. Only horizontal winds are seen. These horizontal winds flow almost always parallel to the Earth's surface. Above the stratosphere, temperature neither decreases nor increases with height up to some level. This small layer is called stratopause. Now, the third layer of atmosphere, that is mesosphere. The mesosphere starts from the edge of the stratopause just at an approximate height of 52 kilometers from Earth's surface. It extends to the height of 80 kilometers from the ground. In this layer, temperature decreases with height as in troposphere. At the uppermost limit of mesosphere, temperature becomes minus 80 degrees centigrade. This layer is called mesopause, above which temperature increases with increasing height. While the composition from the troposphere to the mesosphere is fairly constant, above a certain point, air is poorly mixed and becomes compositionally stratified. The point dividing these two regions is known as the turbopause. The region below is the homosphere and the region above is the heterosphere. Now the thermosphere. The part of the atmosphere beyond mesopause is known as thermosphere, wherein temperature increases rapidly with increasing height. It is found approximately above 80 kilometers from the Earth's surface. It extends to the edge of space at about 60,000 kilometers from the Earth's surface. Temperature keeps rising with altitude in this layer. It is estimated that temperature at its upper limit reaches 1700 degrees centigrade. Thermosphere is divided into two layers, that is, ionosphere and exosphere. The ionosphere extends from 80 kilometers to 640 kilometers. There are a number of ionic layers at various heights in this sphere. For example, D layer, E layer, F layer and G layer. D layer is between the height of 60 kilometers to 99 kilometers and reflects the signals of low frequency radio waves but absorbs the signals of medium and high frequency waves. This layer disappears with the sunset because it is associated with solar radiation. E layer is confined in the height between 99 kilometers to 130 kilometers. This layer reflects the medium and high frequency radio waves back to the Earth. This layer is produced due to interaction of solar ultraviolet photons with nitrogen and nitrogen molecules, and thus it also disappears with the sunset. F layer is generally found at the height of 150 kilometers and is produced due to reaction of ultraviolet solar photons with oxygen molecules, and thus this layer also disappears during nights. These layers reflect medium and high frequency radio waves back to the Earth. The E and F layers also reflect radio waves and have influence over radio communication. G layer is found at a height of 400 kilometers and above and most probably persists day and night but is not detectable. In the upper thermosphere, further concentration of ions is seen that comprises the Van Allen radiation belts. It is named after its discoverer James Van Allen. This layer is sometimes called magnetosphere. Thermosphere as such has no definable upper boundary and gradually blends with space. The exosphere represents the uppermost layer of the atmosphere and outer space begins after it. The air density is very low in this zone and the atmosphere resembles a nebula because it is highly rarefied. The temperature becomes 5568 degrees centigrade at its upper limit, but this temperature is entirely different from the air temperature of the Earth's surface as it is never felt. It is mainly composed of hydrogen and helium. The particles are so far apart that they can travel hundreds of kilometers without colliding with one another. Dear students, now we will discuss the role of atmosphere. The atmosphere contains various gases like oxygen, carbon dioxide, nitrogen, etc. Plants require carbon dioxide to survive, while animals and many other organisms need oxygen for their survival. The atmosphere supplies these life-supporting gases. All life forms need a particular range of temperature and a specific range of frequencies of solar radiation to carry out their biophysical processes. The atmosphere absorbs certain frequencies and lets through some other frequencies of solar radiation. In other words, the atmosphere regulates the entry of solar radiation. The atmosphere also keeps the temperature over the Earth's surface within certain limits. In the absence of the atmosphere, extremes of temperature would exist between day and night over the Earth's surface. In the absence of atmosphere, harmful ultraviolet radiation would find its way through. The atmosphere also takes care of extraterrestrial objects like meteors, which get burnt up while passing through the atmosphere due to friction. Weather, that is the day-to-day state of the atmosphere, is another important phenomena which dictates the direction of a number of natural and man-made processes like plant growth, soil formation, and human settlements, etc. Earth's atmosphere plays an important role in biogeochemical cycles in the Earth's system. It helps in dispersal of spores, pollens, seeds, etc. The ionosphere reflects the radio waves back to Earth for long-distance communication due to presence of ions and free electrons in this zone. The burning of fire takes place in presence of oxygen. Dear students, this is all about structure, composition and role of atmosphere. Thank you very much. God bless you.